Systems VVT Methods, Testing, presented by Ricardo Alvarez, Elizabeth Artalejo, Jessica Coria, Aaron Flores, Jason Jabalie, and Luis Medina. In this presentation, we will discuss white box system testing and black box system testing, specifically black box basic testing. Both types of testing help VVT engineers by dealing with actively operating the system and verifying or validating it. System specifications and requirements dictate what the system should and should not do. System requirements also help to generate the test cases needed to verify and validate the system. The test engineer then performs a testing process specified to system specifications. These system specifications are then used as a measure by which the system should be judged. White box system testing. White box testing is referred to as structural testing. Conducting this type of testing requires the VVT engineer to have an implicit knowledge of the system's inner workings. White box testing invariably demands that the test engineer select test case inputs that will exercise all paths and determine the appropriate output. The two types of white box system testing that we will discuss in this presentation include component and code coverage testing and interface testing.
Component of code coverage testing. In software, code coverage testing refers to a process of verifying that a certain set of input patterns has traversed the entire unit. This testing can help improve test cases that will increase code coverage over vital functions. Of the many types of software code coverage, three are the most popular ones: statement coverage, branch coverage, and condition coverage. In statement coverage testing, we verify that one or more test patterns causes the execution of each and every software code statement at least once. In other words, given a range of initial values or inputs, can the code pass through every single line of code in the program? Branch coverage. In branch coverage testing, we verify that one or more patterns cause the execution of each and every branch of the control flow at least once. In other words, given a range set of initial values, can the code pass through every single option in my program? Lastly, we'll talk about condition coverage. In condition coverage testing, we verify that one or more test patterns causes the execution of each branch of the control flow, and all values of constituents of compound conditions are exercised at least once. In other words, given a range of initial values, can the code pass through every single option in my program, and every set of conditions can be tested at the same time.
Hello, my name is Jason Jabalie, and the next section that will be discussed is interface testing. Before we can understand about interface testing, we must know what an interface is. According to the book, an interface is an agreed-upon mechanism for interaction and communication between different parts. The main reason we perform interface testing is because it evaluates whether systems or components are interacting properly. Interface testing can be broken down into four subcategories of testing. The first subcategory is material interfaces, which identify the need of material exchange between two elements or systems. The second subcategory is spatial interfaces, which identify a need for adjacent force transfer or orientation between two elements. The third subcategory is energy interfaces, which identify requirements for energy transfer between two elements. The final subcategory is information interfaces, which identify requirements for information or signal exchange between two elements. According to the book, many test engineers say that information testing is the most important type of testing in the VVT process. But it is important to remember that all interfaces should be treated with care. Information testing can be broken down into four major classes: hardware to hardware, which is the communication between hardware units; hardware to software, which is the interaction between hardware and software; software to software, which is the communication between software components or subsystems, and human to system, which is the interaction between users and a system. There are three major errors that might happen when conducting testing on interfaces. The first one is interface misuse. It is generated when one component or system does not follow the prescribed interface rules. The second one is interface erroneous assumptions. It is generated when one component or system makes erroneous assumptions about the dynamic behavior of the other systems. The third one is interface timing error. It is generated when the calling and called component operate at different speeds and obsolete information is being used. Now I will be talking about hardware and software testing. In hardware testing, there should be testing performed at several different interface layers. The first layer to be tested should be the physical level interfaces. This testing should be performed on the physical connections between different parts of the system. The second layer to be tested should be the electronic level interfaces. This testing should be performed on the electrical and electronic compatibility of hardware units in terms of signal voltage, current, duration, and shape. The third layer to be tested should be the protocol level interfaces. This testing should be performed on the internal structure and format of signals between two or more hardware systems. Moving to software testing, it allows for the proper transfer of data and should be tested in these common interfaces. The first interface that should be tested is the parameter interface. It is based on the protocol whereby a calling procedure or routine transfer control to another procedure together with a predefined set of parameters. The second interface that should be tested is the message passing interface. It is based on a protocol whereby one procedure or routine may pass messages to another procedure. The final common software interface that should be tested is the shared memory interfaces. They are based on an agreement between one software element and one or more other software elements, whereby one procedure or routine may write predefined information into an agreed memory space, and the other procedures may read it when they are executed. To conclude white box testing, I will be talking about human system interfaces. Human system interfaces are difficult to test since systems can be complex, constantly changing, and information about system operations can be tricky to understand. So it is important to consider the following information when testing. The first thing to consider is unpredictability of users. This testing must cover the variability among individuals. Often modeling differences in human behavior can be difficult to achieve. The second thing to consider is the system missions. Today's engineered systems are expected to perform large varieties of tasks necessitating an enormous range of interactions carried out through human system interfaces. The third thing to consider is the system technology. Modern systems tend to evolve fairly rapidly. The final thing to consider in human system interfaces is the operational environment. Human system interface testing must consider the physical layout of the system at hand. In this image, we can see where the human elements of the system interface with the machine elements. This happens when the human-operated controls of the MRI machine are then turned into input data, and again when the output data of the MRI machine are then turned into information for the human to interpret. To finish off this section, these are some heuristics that should be remembered when dealing with human system interfaces. Keep things simple and natural. Have minimal user memory load, and make handling user errors easy.
Black box testing. Black box testing is referred to as functional or behavioral testing. Conducting this type of testing does not require the VVT engineer to have an implicit knowledge of the system's inner workings. Black box testing presents a series of inputs to a system and compares the outputs to a predefined test specification. There are many types of black box testing, however in this presentation we will only focus on the types of black box system basic testing, which includes boundary value testing, decision table testing, finite state machine testing, and human system interface testing.
Boundary value testing. Purpose. Boundary value testing is a method to verify the behaviors of systems at operating boundary areas by selecting test data values that lie at operating extremes. Boundary test values may include maximum or minimum values within the normal operating domain, values just inside and just outside operating domain boundaries, typically encountered operating values or a specific error condition operating values. Rationale. The objective of this method is to test systems at boundaries of the operating domain where a substantial number of errors tend to concentrate. Generally, this method is applicable to software embedded systems and systems that contain some software components. The weakness of boundary value testing is that the testing process is not exhaustive and the method is not appropriate for complete validation of a system. Method. The boundary testing method is based on selecting test cases within sets of equivalence classes at the edge of the class rather than selecting any element at random. As a result, this method facilitates a possible reduction in the number of test cases relative to the number of detected errors. In summary, the system is not fully validated by a high proportion of errors can be found. The method entails two-step operation. 1. Defining the equivalence partitioning, and 2. Generating and executing test cases at extreme ends of equivalence classes. Step 1. Identifying equivalent classes. This step entails dividing the input domain into equivalent classes of data. Under equivalence partitioning, we define a test case that uncovers classes of errors, thereby reducing the number of test cases required. In other words, an equivalent class. An equivalent class represents a set of valid or invalid states for input conditions. Customarily, we can identify either 2 or 3 of equivalent classes. A. If an input condition specifies a range of values, then 1 valid and 2 invalid equivalence classes will be defined. For example, a month and a year. Valid range 1 less or equal to month, less or equal to 12. Invalid range 1, month less or equal to 0. Invalid range 2, month greater or equal to 13. B. If an input condition specifies a specific value, then 1 valid and 1 invalid equivalences class will be defined. For example, the height of an aircraft above ground in meters. Valid range 0 less or equal to object height. Invalid range object height less than 0. C. If an input condition specifies a set of values, then 1 valid and 1 invalid equivalence classes shall be defined. For example, names of family members. Valid range Tom, Norma, Peter, Amanda. Invalid range X, 77, or Sophia. Step 2. Boundary value testing. Applying boundary value testing requires a selection of test cases at each side of the boundary between equivalent classes. That is, for a valid range of values bounded by a minimum A and a maximum B. The test case values should be A minus 1, comma A, and B, comma B plus 1. Therefore, in the above first example, a month specification within a date input stream will entail selecting test data of 0, 1 for the lower boundary, as well as the second test data of 12, 13 for the upper boundary. All told, testing will be done by means of 4 test cases where each of these pairs consists of a clean and a dirty pair. Clean tests should result in a valid operation, whereas dirty cases should result in error treatments. More specifically, in case of HSI, the system should issue a warning message and a request to enter the correct data. Along the same line, the above second example, a height specification will entail selecting test data of -1, 0 for the single boundary. That is, testing will be done by means of 2 test cases. Similarly, in the above third example, names of family members will entail selecting test data of the entire valid sets. Obviously, the invalid range in this case is indefinitely large and therefore reasonably judgment
Reasonable judgment must prevail as to the appropriate number of required invalid test cases.
Decision table testing. This testing technique becomes important when it is required to test different combinations. The decision table can be used when the system behavior is different for different inputs and not safe for a range of inputs. Decision table testing method focuses on validating responses of a system under specified conditions and constraints. System testing is accomplished by a means of a decision table, which is a precise and compact way to model complicated logical behavior. Decision tables are typically divided into 4 quadrants as depicted in the table below. The table will contain the conditions, conditions alternatives, actions, and action entries. The representation is simple so that it can be easily interpreted and is used for development. This table will help to make effective combinations and can ensure a better coverage for testing. Construction of a decision table is accomplished using the following steps. Step 1. Identify all the possible conditions and or combinations that could affect the behavior of the system. Step 2. For each and every condition identified in the first step, define all the possible system actions in response to these conditions and their combinations. A typical decision table structure is divided into 4 quadrants. When analyzing the figure that was in the previous slide, each condition corresponds to variables whose values are listed in the condition alternatives. Each action is an operation performed by the system under the stated conditions. In decision table testing, each condition corresponds to variables whose values are listed in the condition alternatives. Each action is an operation performed by the system under the stated conditions. To the right of the slide is a table created to test our autonomous shuttle bus system operation. The upper left quadrant of this table states the possible conditions that our system will face. Condition 1, non-hazardous weather. Condition 2, rainy weather. Condition 3, snow or icy conditions. Condition 4, physical obstruction. The lower left quadrant of the table states that actions that our system is possible of taking. These actions are to operate as normal, reduce the shuttle bus's speed, or unable to operate. In order to fully test our system, we will have to test all possible conditions and ensure the correct actions are taken. In the upper right quadrant, we will denote itself as true or false. This is displayed as a letter T and a letter F. If the quadrant is blank, it is denoted as not available or do not care. We can view the first 2 combinations to get a better understanding of how this system works. If the system is functioning through non-hazardous weather, a letter T will be placed in the first combination, since it is true. The action that will then be taken is to operate as normal, which is identified with the letter X in the lower right quadrant. Moving on to combination 2. If the system is having to operate in rainy weather, the non-hazardous role will be marked as false with the letter F, and the rainy weather condition will be marked as true with the letter T. The action that will then be taken is to reduce the shuttle bus's speed, which is identified with the letter X in the lower right quadrant. This process is then followed for all the possible conditions and their combinations that could affect the behavior of the system. By using this method, you will ensure a better coverage for testing. Finite state machine testing. The purpose of this type of testing is to evaluate systems for proper execution of control functions. Finite state machine testing is based on the automata theory, which studies automata and the computational problems that can be solved using them. FSM testing models the dynamic behavior of complex systems. These models have a finite number of states and transitions between those states. All engineered systems have an initial, or power-up state, an operational state where the system's activities are performed, and a final, or power-off state. FSM models are made up of states and transitions. A system will remain in its current state until a specific external input or internal event occurs. After the input or event occurs, the system transitions into a different state. Activities are associated with specific states and typically produce specified outputs. FSM testing helps to identify any area of failure relating to state-event combinations, transition structure, or paths specified by the state machine. FSM testing tests for errors. Some include action fault, when the actions on transitions are incorrect or missing, unspecified event or missing transitions, where there is no transition specified for an event, unintended failure, where the system accepts an event which should not be accepted, and next state fault, where the system transitions into the wrong state. The state transition table shows all possible outcomes that result from combinations of the inputs and states in the state diagram below. This is an example of an FSM testing model for an autonomous bus that uses image recognition software to detect for obstructions in the road. There is an initial state where the bus is not yet in motion, an operational state where the bus accelerates, decelerates, or remains at a constant speed, and a final state where the bus changes into manual mode and is no longer autonomous. The transitions are represented by numbers and are the only possible inputs at that given state. 0 represents no obstruction is detected, and the bus can accelerate or remain in motion. 1 represents an obstruction is detected, and the bus can remain in its start state or transition into the deceleration or manual states. 2 represents the switch to manual override. FSM testing helps us map the possible input state combinations and their outputs. It shows us where and what type of failures may occur for the system.
Human system interface testing. The purpose. The purpose of this testing method is to validate that the HSI is functioning properly from both the ergonomic and the functional point of view. HSI testing should consider both the input as well as the output boundaries between people, operators, and users of systems and the system itself. The HSI is the interaction of humans and engineered systems via input from the human to system and output, which displays feedback information to the human user. Rationale of HSI. The discipline of HSI deals with the boundary area between humans and engineered systems. More specifically, HSI deals with input devices, which are means by which humans control systems, and output devices, which are the means by which humans interpret systems information. HSI performance determines how easily a user may control and comprehend the underlying functions of a given system. Testing HSIs concentrates on 2 aspects: the proper functioning of the interfaces and the ergonomics of interface activities. Ergonomics focuses on people's abilities and limitations, as well as what they must do in order to deal with or operate the system. The objectives of ergonomic design activities are to optimize the effectiveness with which work and other human activities are carried out. Testing for proper HSI ergonomic design will assure easily manipulated operator control interfaces and clear and intuitive representation of system conditions. This will decrease the probability of operator mistakes and misinterpretation of system conditions. Moreover, HSI ergonomic testing increases the likelihood of cost savings in operator training and knowledge retainment. Testing HSIs is also the process of evaluating user input into the system, as well as system input to ensure that the system satisfies the specified requirements. Method. The method is the concept by which humans interact and control a system via any type of interface that must be capable of receiving commands, and relay back the information. These are referred to as HSI devices. Command take many forms such as switches, keyboard strokes, mouse movements, screen touches, voice commands, etc. Monitors provide humans with the information they need to control the system. Below is a table with the range of selected HSI devices. Human input testing. In order to test a human input interface, there are two main aspects that must be tested. 1. Validate that the system responds correctly to proper commands or sequences thereof. 2. Verify that the system recognizes, tolerates, and properly handles operator error. Combining both actions and the requirements that the quote-unquote, the system is able to properly process both expected and unexpected input values. The test engineer must select data that shows the presence of a tolerance range of expected and unexpected input values. In general, tolerance properties of a system should be able to handle 1. Detect and handle proper user inputs. 2. Detect user input errors. 3. Stop input errors from propagating beyond the HSI area. 4. Indicate the existence of input error to the user. 5. Provide some further suggestion about the nature of the input error and how to correct the error. Validating system response. In order to validate error handling response by the system, invalid input sequence and illegal text commands are generated. The following are an example of system evaluations. Violate data type or size. Violate user input restrictions. Skip mandatory fields. Inundate system. Generate unexpected sequences. Human output testing exceptions. Another way to discover system weaknesses is to study how a system issues an exception to a user. In other words, it is an event that signals that an error condition has occurred during the running of the system. The following strategies highlight a system's response check to illegal human commands. Real-time validation. After each keystroke, mouse interaction, or switch activation, the system checks to see whether the input meets an expected value or event. Otherwise, the system issues an exception. Committed value validation. After the user has filled out a given field completely and commits his entry, for example by pressing a key to move to the next field, the system checks whether the entire input field meets expected values. Otherwise, the system issues an exception. Pass-through validation. After the user has filled out an entire form and commits his entry, for example by pressing the carriage return key, the system checks all the fields in the form at once and issues exceptions for the invalid fields. Human output testing. HSI testing involves generating and executing test sequences intended first to verify that the system meets the specifications and second that humans react properly to the output information. Testing human output interfaces dependent on the specifics of the system and its output devices. The following describes such testing by means of a simple example in the context of a typical Windows operating system. Selection box. All relevant destinations are available for selection in the destination field. Radio box. There are only two possible types of flights available, for example, scheduled and unscheduled, and only one type of flight can be selected. Checkbox. There are two possible types of payload available, for example, passengers and cargo, and either one or both may be selected as depicted in the payload field. Buttons. Pressing the enter button will activate the flight plan, and pressing the cancel button will terminate the request without activating the flight plan. Inundate system. Attempt to write extremely long text string into the pilot name field and see what appears in the field. Violate data type or size. Attempts to insert into the pilot name field characters which are outside the 26 alphabet character set. For example, numbers, punctuation marks, control characters, etc. Violate user input restrictions. Attempt to write a random text string into the destination field, see what happens in this field. Attempt to select or unselect both radio buttons in the flight field and see what appears in this field. Skip mandatory fields. Do not select any checkbox in the payload field and see what appears in the field.